We've already seen different methods for solving differential equations, but in this video I'll present to you a new method called the power series solution method, which consists of trying to write our solution, y of x, as an infinite series. So we have a summation, and n goes from 0 all the way to infinity. So it's an infinite series, but it's an infinite power series, because we raise x to the power of n. And our goal will be to try to find the coefficient c of n, to try to find an expression of Cn. In the next video, I'll be explaining when we can actually use a power series solution to solve our differential equations. Indeed, we can't always use a power series as a solution to our differential equation. We will see that our differential equation needs to satisfy certain conditions in order to use this method. But let's explore the power of this power series solution method by looking at a specific example. We'll be looking at the example x y prime is equal to y. And this is a first order linear differential equation. And you can use the separation of variables technique to solve this equation. However, in this video, I'll be using the power series solution method in order to show that it works. In essence, we plug this trial solution, which is a power series, into our differential equation, and we want to see what conditions our coefficient c of n needs to satisfy in order for y of x, this power series, to be a solution. So we already have y of x over here, so we need to know the expression for y prime. In order to do so, let's write out the first terms of our power series, y of x. So we have, for n is equal to 0, c0 times x to the power of 0, which is 1, plus c1 x to the power of 1, and then c2 x squared, and so on. Now, if we differentiate this expression, we get, so the derivative of c0 with respect to x is 0. So we get 0 here, plus the derivative of c1x is c1 plus 2c2x, and so on. And more generally, the derivative of c subscript n times x to the power of n is n times c of n times xn minus 1. This is just the power rule for derivatives. And therefore, to calculate y prime, well, we just use this expression that we have over here. So, n cn x to the power of n minus 1. And we have, of course, an infinite sum. So, infinity and n is equal to, well, what should be the index, the start of the index over here? Well, notice that when we differentiated the first terms of our series, we started from c1, because c0, its derivative of 0. So n doesn't start from 0, but from 1. And so this is the derivative of our power series. And in general, it's always important to first calculate the derivative of our first terms in our infinite series in order to get a general expression for the derivative. Okay, so for example, here, I wrote down the first terms of our series. I noted down that our derivative starts from c1, and therefore the index n starts from 1. And in general, the derivative of cn times x to the power of n is this expression. So I wrote it down over here. And now what we do is we sub in our expressions into our differential equation. And the key thing here is that we want the exponent of x on both sides of the equality to be equal to each other. But the problem here is that we have an n minus 1, and here we have an n. And so it's hard to equate these two equations if we don't have the same exponent, because we can't identify common factors. And so what we do is we absorb the x over here, because here x is x to the power of 1. So if we sort of absorb the x into our summation, we get 1 plus n minus 1, which is n. And that's what we want. Therefore, we have the infinite sum of n going from 1 to infinity of n Cn x to the power of n is equal to the infinite sum, and going from 0 this time to infinity of Cn x to the power of n. One final thing we need to do before comparing these two summations is that we need to have the same start of index over here. In the left side, we have that n starts from 1, but on the right side, we have that n starts from 0. And so what we do is we write down the first term of our summation on the right, which is, well, C0 plus the infinite series. But this time n goes from 1 to infinity of Cn x to the power of n. But the problem is we still can't compare these two sums because we have an isolated C0 over here. But notice that if we plug in x equal to 0, well, this would mean that we have 0 is equal to C0. And therefore, we have the expression for our first coefficient in our power series solution. And therefore, this simplifies to this equation. And the coefficients that multiply x to the power of n have to be equal to each other. So n times Cn has to be equal to Cn. So n times Cn is equal to Cn. And this is only true in two cases. The first case is when Cn is equal to 0. But this is a trivial case because this would mean that y would be equal to 0, but we're not really interested in a trivial solution. So another solution is when n is equal to 1. And therefore, this sort of truncates our series because all we're left is n is equal to 1. And so instead of having n being an integer going from 0 to infinity, we only have 1, n is equal to 1. And therefore, our solution to our differential equation is y of x is equal to C1 times x to the power of 1. So C1 times x. And so this is our solution to our differential equation. And in order to verify this, let's use the separation of variables method to solve this differential equation. So without using a power series. And so we get that y prime divided by y is equal to 1 over x. And by integrating on both sides, we get that ln of the absolute value of y is equal to ln of the absolute value of x. And therefore, y is equal to kx. And I can't forget about the arbitrary constant here when we integrate it here. That's why we get a constant. And this fits exactly with the solution we got using a power series. And this is what we expected. We expected the power series method to give us the right answer. And notice here, I've called the arbitrary constant C1 instead of K, but we can call the constant whatever we want. So the next videos will focus on how to use the power series method to solve more difficult differential equations. But to quickly recap what we do, is we use a trial solution, y of x, which can be written in the form of a infinite power series. And we plug this power series into our differential equation. And we try to see what expression or what conditions c of n has to satisfy in order for y to be a solution to our differential equation. And that is it.